Welcome to qnawire.
This is Chapter 22, Problem 10 from the Sears and Zemansky's University Physics textbook. A point charge Q1 equals 4.00 nanocoulombs is located on the x-axis at x equals 2.00 meters, and a second point charge Q2 equals negative 6.00 nanocoulombs is on the y-axis at y equals 1.00 meters. What is the total electric flux due to these 2 point charges through a spherical surface centered at the origin and with radius A, 0.50 meters, B, 1.50 meters, and C, 2.50 meters? All right, the very first thing that I have done is I have made a sketch of the x and y axes. So at x equals 2 meters, so just going along the x-axis, that's where our charge Q1 is located. And going up along the y-axis, at y equals 1.00 meters is where our Q2 is located. And then I've drawn out the 3 parts that we're looking for. So first we have a sphere of radius 0.500 meters. So that's coming out from the origin. We have this red circle. In part B, we're looking at a radius of 1.50 meters. So I've drawn this one out. So a little bit further. And the radius for the sphere of 2.50 meters, then I've drawn this one here. So I've color coded each of these so it's easy to keep track of which one's which. Part A is in red, part B is in green, and part C is in blue. So the key to this problem is we're simply applying Gauss's law to the spherical surface. Also, my apologies, each of my circles here aren't really good circles. I am limited in my artistic skills, but you should get the general idea. All right, so we're just using Gauss's law, which says that the net electric flux through any surface is simply equal to how much total charge is enclosed in that surface divided by epsilon naught, which is our universal constant for electricity. And epsilon naught is 8.85 times 10 to the negative 12 coulomb squared per Newton meter squared. All right, the first one in part A, well, we look at that surface, and because it only goes out to 0.50 meters, it doesn't include any of the charges because Q1's out at 2 meters away, and Q2 is at 1 meter away, so nothing is enclosed in this surface. So the total enclosed charge is 0, therefore the net electric flux through the surface in part A is just 0. There is no flux through that surface. In part B, the total enclosed charge, well, this is a radius of 1.5 meters, so that includes our Q2 charge because 1 meter is included in the radius of 1.5, but it doesn't include Q1. So the total enclosed charge is just Q2, which is negative 6 nanocoulombs, which I've already written out. Nano is 10 to the negative 9, so it's negative 6.0 times 10 to the negative 9 coulombs. So I plug that in for the total enclosed charge Q2 divided by epsilon naught, and when we plug the numbers in the calculator, we get negative 678 Newton meters squared per coulomb for part B. And then part C is the total enclosed charge at 2.50 meters. Well, that circle includes both Q1 and Q2, so the total enclosed charge is simply Q1 plus Q2. So the net electric flux is Q1 plus Q2. This total net charge divided by epsilon naught. So we sum 4 times 10 to the negative 9 plus negative 6 times 10 to the negative 9 coulombs. So we have that total enclosed charge divided by epsilon naught gives us negative 226 Newton meters squared per coulomb. So we see the net flux then depends only on the net charge that's enclosed by the surface, and it's not affected by any charges outside of the enclosed surface. So even though in part A we have Q1 and Q2 are outside, but they don't contribute to the net flux going through the surface. Only what's enclosed by the surface of whatever charge is enclosed within the surface that we're interested in. So this is just a basic exercise. Just we use Gauss's law and we just plug in the value for the total enclosed charge in each specific situation in order to get the total final answer for the net electric flux through the corresponding surface.